In this video, we're going to start to look at bonding in diatomic molecules, and we're going to see ways that you can consider bonding incorporating some quantum mechanical ideas that we've met earlier. So let's consider initially a homodiatomic molecule. So let's initially start with so homo means same, so it's just two atoms of the identical type. And we're going to consider two atoms of the same type that are close together and far apart. So let's consider initially they're far apart. And then they're going to be close together. Okay, so when they're far apart, we can imagine if this is hydrogen, for example, we have a hydrogen atom, let's call it hydrogen atom A. We have another hydrogen atom, let's call it hydrogen atom B. And we could say, if we were to represent this system, a wave function of this system, we could say that the wave function of this system has to incorporate hydrogen A and hydrogen B. So we could say that, well, first of all, it's going to be the wave function of hydrogen A. Now, hydrogen A only has one electron. The electron is in a 1s orbital. And let's say that the electron, I'll use red if I can find my red pen. So the electron, we'll call it the number 1. I want to give the electron a number so that we can keep track of who is the rightful owner of that electron. So the electron, let's say, is the number 1. And I've also got a wave function for hydrogen B. The electron is in a 1s orbital, and let's say it's electron 2. So I'll write the number 2 here. So if I had to look at the overall system, so let's call this capital psi, it would be this product here. So again, when these hydrogens are far apart, we can make some assumptions. We can assume that electron 1 is on hydrogen atom A, and we can assume that electron 2 is on hydrogen B. Okay. However, things can change when they're close together. For one thing, that if they're close together, they can form a bond, but we're going to see the argument that would be behind them forming a bond. Okay, so when they're close together, so we'll physically draw them closer together. HA and HB. So when they're physically close together, it's true that electron 1 can be on hydrogen A and electron 2 can be on hydrogen B. But also, if they're close enough together, we draw hydrogen A and hydrogen B again. If they're close enough together, electron 2 can be on hydrogen A and electron 1 can be on hydrogen B. So it's this shuffling around of the electrons that now becomes possible if they're close enough together. So we can say if they're close together, it's possible that electron 1 is on hydrogen B and electron 2 is on hydrogen A. So that becomes possible, and that possibility is what makes the bond. The lack of possibility when two things are far away in space is what makes it implausible that there's a bond. So we can write something about our previous statements. So we know from quantum mechanics we superimpose these two equally likely possibilities and these two equally likely possibilities I'm referring to are the fact that hydrogen A's electron can be on hydrogen B and vice versa, hydrogen B's electron can be on hydrogen A. And we write that as the total wave function psi of the system, hydrogen A, which we now believe is bonded to hydrogen B. So here this represents a bond when they're close enough together. So we would say it's the wave function psi of hydrogen A. It's 1s electron, 1s orbital electron I'm calling number 1 as a product with wave function psi of hydrogen B. It's 1s electron, and it's 1s orbital. I keep saying 1s electron. It's 1s orbital with its electron I've called electron 2, and because we're superimposing, so we're going to add, so we add the opposite possibility, which is that we have the wave function for hydrogen A, it's 1s orbital, but now with electron 2, and the wave function for hydrogen B, it's 1s orbital, this time with electron 1. So we take the two possibilities and we add them. And this has a striking consequence. So therefore we cannot differentiate or we cannot distinguish the exact location of either electron 1 or electron 2. Which is great, and that totally agrees with Heisenberg's uncertainty principle. You can't pin an electron down, or any subatomic particle for that matter. And in general, we can write an expression, and I'll write the general expression and then I'll comment for those of you that might have seen my video on Pauli exclusion principle, you might be worried that I have a plus sign here rather than a negative. I'll clarify that in a second. I don't want that to be any source of confusion. So in general, we have the overall wave function for a homodiatomic molecule, which let's say is A and B, is just the wave function of A for particle 1, the wave function for B, particle 2 here, the particle is an electron, plus the wave function for A with the reverse particles, particle 2, the wave function for B with particle 1. Okay, so this is in general, and actually this would apply to not just homodiatomic, but for any diatomic, whether it be homodiatomic or heterodiatomic. Okay, so before we clean this board up and move on to our next board, I just want to clarify why we have a positive sign here. So if you recall my video on Pauli exclusion principle where we had something called the Slater determinant, if you don't recall that, go back and look at my video on Pauli exclusion principle. Having done that and now coming back again, we had a negative sign here. Recall that in that video we were arguing the spin, the spin wave function. Here we're looking at the space wave function. So if ever we're talking about the spin wave function or the spin state, we'd have a negative sign here. That's Pauli's argument. Here we're looking at space, so it's going to be positive. So they're two different things. So I wanted to make that clear. So let's move on to look at what can happen in these bonds, whether they be homodiatomic or heterodiatomic. We're going to take a linear combination of atomic orbitals, so essentially two separate atoms which would have atomic orbitals, and we're going to take a linear combination, which means we just combine superposition. So when I earlier said superposition, that would be a linear combination. But we're going to then go from the atom to the molecule. So a linear combination of atomic orbitals then gives us information about the molecular orbital, which essentially is what we have. So just to reiterate what we've discussed already, we said that if an electron can be found in an atomic orbital belonging to atom A, and also in an atomic orbital belonging to atom B, then the overall wave function psi is a superposition of those, linear combination or a superposition of those atomic orbitals. So to put that in a general form, we can say that overall this wave function psi, well actually to put it in a general form, but to extend it now into a more powerful theory, it can actually be positive or negative, and we'll see why. And it's going to be a coefficient n, a plus or minus b, where a and b could be the same, but a and b can also be different. So a can equal b, or a cannot be equal to b. So for now, a and b are just labels. N is a normalization factor. So we won't quantify the normalization factor, but we know we have to include one. If you recall back to the videos on the quantum mechanics chapters for general chemistry, we know that the wave function, when we take real world interpretations of it, we have to take we have to square it, and we interpret that as a probability. So when we take the square of psi, it leads to a probability of location or localization. And because we have probability, the probability has to be normalized so that it can't be above 1 or 100%. So anyway, it's just something that we need to keep the numbers sensible, but we don't need to worry about its quantification. Okay, so this implies, seeing as we're going to take the psi squared, this implies that psi squared, if we take the plus case, so just the plus case, then we have the square of the normalization factor, n squared, and then we have the square of this bracket, which is just a plus b squared. So that's equal to n squared, and then I have a plus b squared. Well, I have to FOIL that out. So that's going to give me a squared plus b squared plus twice ab. So if I do the parentheses and I square that out. So notice I have the possibility that the electron, A's electron can be on A. I also have the possibility or the probability that B's electron can be on B. But I also have this interference term where I've got a mixture of A and B now. So this is the interaction or the bond. And these are for bonding orbitals. So this whole expression is for bonding orbitals. Again, you can interpret this as interference. You can call that a bond if you like. So if we were to plot this out, we would have, for example, let's say this is the location if radius r is distance from the nucleus. So this is the nucleus center here. So this is a plot of psi squared without, so lowercase psi squared for, let's say, well, it doesn't have to be h, let's just keep it general and call it a. Okay, and then we could have, I'll do it in red. Again, let's say this is the nucleus, this is the radial probability of finding the electron. Let's call this B. So remember, psi squared is interpreted as the probability of localizing the subatomic particle that you're looking at. Here we're talking about the electron. Notice that there's a non-zero probability here. This is greater than 0. So there would be a positive overlap here, this positive interference piece here, this 2AB. So this would just be so A essentially bonded to B. Where here psi squared is greater than 0. So we interpret this psi squared is greater than 0, which implies essentially electrons or electron density is now located between A and B. And that location of electron density between, that's what we mean by a bond. So these are how orbitals would bond. We're going to contrast this with what happens when psi squared is negative when I clear the board. So we're going to go back now and look at what happens when psi squared is negative. So when psi squared is the negative case, then we'd have n squared a minus b squared, which would be n squared, the normalization factor, and then we'd have a squared plus b squared minus 2ab. So the only difference here is we have this negative sign here, whereas previously we had a positive sign. So we have an interference term, but essentially it's a negative term. So we call this anti-bonding. So this would be the anti-bonding case. So there are flavors of bonding, both bonding and anti-bonding. If we were to look at the psi squared, then again we would have, let's say A, he is the nucleus, he is the radial probability of finding the electron, and B would be here, and if I've drawn it to show you what I want to, there's zero probability above that line. And actually what I could do to make it look a little bit more realistic is slightly raise that up a bit. So that there is a positive value here and there is a positive value here. So this would imply that there's absolutely no so psi squared is exactly 0 between the nuclei of A and B. So there's no probability of finding electron density. And in fact, again, I should have rigged that to make it look a bit higher here and a bit higher here. Not only is there no interaction here, but because this is a little bit higher here, there's a little bit of kurtosis, I guess, if you like. Then actually you've got more electron density here, so the nucleus is going to be pulled that way. So there's going to be a force here where the nucleus is being pulled this way by its electrons, which are over here. And likewise, this nucleus is being forced this way. So we actually have more electron density outside of the internuclear region than we do between the internuclear region. So there's a force on the positive nucleus pulling it away. So not only is anti-bonding not only is that the lack of a positive interaction, there's actually a positive repulsion. So typically an anti-bonding orbital is destabilized, so we can write it as a higher energy orbital, whereas a bonding orbital is stabilized because we have this positive or favorable interaction that we'd have to overcome if we wanted to separate them again. So we have this concept when we combine atomic orbitals, when we superimpose them linearly to form molecular orbitals, they can either interact favorably or unfavorably. Favorable interaction forms bonding orbitals. Unfavorable interaction forms anti-bonding orbitals. So we've seen that we can take a linear combination of atomic orbitals and make molecular orbitals. Now let's go ahead and start to apply this. We'll just look at homodiatomic molecules here. Exclusively just for proof of concept. So the simplicity of looking at homodiatomics is that we can say that these energy levels are exactly the same. So let's say this is just AA. So we've got atom A and we've got atom A. Okay. So we've got two identical atoms. It's a homodiatomic molecule. So I'm going to draw the molecular orbitals in red. So if we've got a linear combination of two atomic orbitals, we should have two molecular orbitals. So linear combination just means add them. So I've got my, I guess this would be the interaction of AA in the middle. So this is my atomic orbital for A, my atomic orbital for A. This is my molecular orbital for AA. And I can have a bonding orbital which is stabilized with respect to the barycenter. So this is stabilized because I've gone down in energy, and this is destabilized. So this would be bonding, and this would be anti-bonding. So these orbitals, rather than call them S, because we associate S with atomic orbitals, we're going to use the Greek letter sigma to represent molecular orbitals. So I could call this the sigma bond formed by a 1s orbital, and I could call this the sigma bond star formed by a 1s orbital. The star represents anti-bonding, the absence of the star represents bonding. Likewise, I can take my 2s and I would form, from a linear combination, I'd form two molecular orbitals. In this case, I would form, again, anti-bonding and bonding. Notice that the anti-bonding is always destabilized with respect to the barycenter, and the bonding is always stabilized with respect to the barycenter. And I could have a sigma 2s molecular orbital versus a sigma star 2s molecular orbital. So we can make this, instead of generic like this, we can actually look at some real homodiatomic molecules. So let's say we want to look at, first of all, we'll look at hydrogen. So we'll look at hydrogen. So hydrogen would have two electrons. A molecule of hydrogen would have two electrons. We've got one electron in the 1s orbital of one of the hydrogens, another electron in the 1s orbital of another hydrogen. So two electrons come together, they're naturally going to sink down into the bonding orbital, and they would form an anti-parallel pair because of Pauli exclusion principle to give them 4 unique quantum numbers. And there's no bonding, there's no anti-bonding presence here, so there's only a bond. So this depth here essentially would be the bond strength. So the enthalpy of the bond, that would be a representation of the bond strength. And if you wanted to break the hydrogen bond, you'd have to pay that energy price to lift the electrons back out again and separate them. We can actually calculate the bond order. So let's calculate, well, first of all, let's look at how you would write the molecular electron configuration. So you would write this as sigma 1s 2. So there's 2 electrons in this molecule. They're both in a sigma 1s molecular orbital, and there are 2 electrons. If we wrote the bond order, which I'll typically just call BO of H2, then the bond order of H2 essentially looks at the sum total of all the bonding and anti-bonding orbitals. So you essentially you add up all of the bonding electrons and you subtract all of the anti-bonding electrons. So the bonding order is going to be 2 bonding electrons, and there are no anti-bonding, so minus 0. And then you take the average. So this equals 2 minus 0 is 2. 2 divided by 2 is 1. So we can interpret the bond order in a couple of ways. We can say that since the bond order is greater than 0, it implies that H2 exists as a real homodiatomic molecule. If for some reason we calculated the bond order and the bond order was 0, that's evidence that there's no interaction, so there'd be no such thing as H2. So the fact that it's greater than 0, we know that H2 exists as a real bona fide molecule. We can use it to quantify the stability. The higher the bond order, the more stable. So we can say a couple of things. The bond order is proportional to bond stability. We can also say that bond order is proportional to 1 over bond length. So in short, the longer the bond, the smaller the bond order. So long bonds tend to be weaker, shorter bonds tend to be stronger. And I'll continue this. We'll try and populate some of the 2s just to give you a feel, but we've at least looked at hydrogen before I clear this board away. So let's go ahead and add 2 extra atomic orbital electrons. So we've got 2 here. So A now is helium. So I'm looking to see for the presence of a helium bond between 2 helium atoms. So I've got 4 electrons total. So we already had 2 electrons coming in here and here. So we have 4 electrons total. So 2 occupy the bonding sigma 1s orbital. The other 2 have no choice but to be promoted to the anti-bonding sigma star 1s orbital. So if we wrote the molecular orbital configuration, we would write sigma 1s2, sigma star 1s2. So there are 4 electrons from our supposed helium molecule. Let's calculate the bond order of helium. Well, that would be the number of bonding electrons, which is 2, minus the number of anti-bonding electrons, which in this case is 2. And then we take an average. So you're essentially looking at average, the net effect of stability and destability, see if there's anything left. 2 minus 2 is 0. 0 divided by 2 is 0. So this means that helium doesn't exist as a diatomic molecule. It doesn't exist because there's no net force keeping it together. So the two helium atoms just perpetually have no interest in each other. So it's not a real molecule. And this is the benefit of looking at molecular orbitals. We'll proceed to look at, after helium, we get lithium. Let's see if dilithium exists. So to look at dilithium, I'm going to clear this up a little bit, and then we'll add one more electron each side. Okay, so to look at dilithium, we know that lithium has 3 electrons total, so I've added the valence electron of lithium to its 2s atomic orbital. So I'm already done with these core electrons. Now I just have to look at the valence electrons. They both funnel down into the sigma 2s orbital. They line up anti-parallel according to Pauli exclusion. And so when I look at the electron configuration for the molecular orbitals of our supposed molecule Li2, we have sigma 1s2, sigma star 1s2, the anti-bonding orbital, and then we have sigma 2s2. So there's my 6 electrons in this molecule, 3 from each lithium. Let's look at the bond order. Let's see if dilithium exists. We have 4 bonding electrons, and we only have 2 anti-bonding electrons. Take the average. 4 minus 2 is 2. 2 divided by 2 is 1. So we know that dilithium does exist, and the only evidence we have, it's roughly as stable as dihydrogen. That's all the information we have right now. We'll go ahead and look at diberyllium, see if that's a real thing. Okay, so diberyllium, if it exists, we'd have 2 beryllium atoms. We've got 4 electrons from each beryllium. So that means I've now gone and added, filled the I filled in the sigma star 2s orbitals, the anti-bonding orbitals. So if I wrote the electron configuration down of these molecular orbitals, it would be sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2. So there's my 8 electrons total. Let's see if it's a bona fide molecule. The bond order, I've got bonding electrons 2 here and 2 here, so that's 4. The anti-bonding electrons, I have 2 from the 1s star and 2 from the 2s star, so that's 4. Take the average, that's 0. So we have evidence, theoretical evidence, that there's no such thing as diberyllium. Okay. So I'll clear this part of the board, and then we'll look at, visualize what these orbitals must do to make these bonding and anti-bonding orbitals. Okay, so what we want to do now is to go in, before we lose this diagram, we want to go in and look at what these orbitals are doing to make the bonding interaction versus the anti-bonding interaction. So we could say that the sigma 1s orbital, what's happening is we've got spherically symmetrical s orbitals, and we could say that they're interacting like this. So I've got the overlap of these 2 spherically symmetrical atomic orbitals, which you could imagine would make some kind of interaction where it's one continuous object where the electrons can, almost like a peanut, I guess, where the electrons can occupy proximity to both nuclei and help bind both nuclei together. Conversely, the anti-bonding, and actually I should have drawn that by the bonding, shouldn't I? So that was ill-advised. So the bonding, this is the bonding. The anti-bonding, remember that there's no probability of locating the electrons between the nuclei. So almost looks like a pair drop, and I'm going to color this in. I'm going to shade it in. There's absolutely no probability of finding the electron, but we have this ability of anti-bonding orbitals to actually repel each other. So this warped bubble of electron density here, this essential wave function squared. So these shapes, these orbitals, remember, they are the psi squared, a visual of the psi squared function. They're actually ballooning outwards. So they're trying to get away from each other. So this would be the anti-bonding interaction, or lack thereof. All the shading means here is the information in these two orbitals is of the same type. And here I'm using shading to represent that the information in this orbital is of the wrong type with this, so there is no interaction. So just interpret the shading here to be the appropriateness of the information, the wave function information to interact. You could do exactly the same for the 2s. 2s would be a bit bigger. I'm not going to bother with the size. You can imagine this being a bit bigger. But you'd have that bonding interaction. Versus this ballooning to try and get away from a neighbor. Because the information is of the wrong type to interact. Okay, so I'll clear this board up and then we'll go ahead and look at p-orbitals. Okay, so now we're going to continue. We've already looked at 1s orbitals and 2s orbitals. Let's go ahead and look at 2p orbitals, just to show proof of concept. And I've split this up into two groups because there's two important families, I guess. The family on the left is going to go from boron through, let's see, nitrogen. So boron 2 to nitrogen 2, it's going to apply. The family on the right is going to go from oxygen 2 to neon 2. So you really have to know which family to apply, and this is going to be the breakdown of which families. Okay, so I'm going to grab my pen. So let's say these again are the atomic orbitals. We're going to have the molecular orbitals in the middle. For this family, diboron through dinitrogen, it follows the following sequence. It's going to be 2, 1, 2, 1. And for the family dioxygen through dineon, there's going to be an exchange of these orbitals. So the 2 and the 1 are going to flip. So it's going to be 1, 2, 2, 1. So there's just an exchange of these two, and that's an important exchange. It's experimentally verified. So let's have a look at the consequences of it. Well, let's start with B2. B2, so we'll take for granted that we've already got the 1s2 and the 2s2 already filled. Boron 2 has now a 2p, so they would flood down into this would be the, well, this wouldn't be sigma at all. First of all, let me tell you how to interpret this. First of all, I've got the 3 p orbitals. Remember, p orbitals, there's 3 of them. There's px, py, and pz. I've written them as a layered structure here. You could have them side by side. Here I've stacked them, but they're all the same energy, and anytime we have orbitals the same energy, we say that they're degenerate. So this is just how I've represented them, and it's a common representation. So these are all exactly the same energy level. I fill them in here. Now notice that I've got 3 plus 3, and they must be conserved. So I've got 2, 3, 4, 5, 6. So 6 atomic orbitals come in, and we get 6 molecular orbitals as a result. Notice they come in clusters of 1 and 2. When we have a cluster of 2, we call them a pi orbital. When we have a cluster of 1, we call it a sigma orbital. So pi and sigma. Anything lower than the barycenter has no asterisk, it's bonding. So this is a pi 2p orbital. This is a sigma 2p orbital. This is a pi star 2p orbital, and this is a sigma star 2p orbital. Okay, so every bonding orbital has an anti-bonding partner. Every bonding orbital has an anti-bonding partner. We add the 2p electrons from each boron atom. They go into the bonding orbital because that's lower in energy and has to be occupied first. We can ignore the core electrons here, the 1s2 and the 2s2, because we know that they sum to 0. So net, we just have 2 net bonding here, so it's 2 bonding. Well, first of all, let's do what I wanted to do originally, which is the electron configuration. So we would have the sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2, and now we've got pi 2p2. So 4 electrons from each boron, 8 electrons total, 2, 4, 6, 8. The bond order, let's find some space, let's do it down here. The bond order of B2, the 1s2 and the 2s2 sum to 0 net. Let's look at the pi 2p. So we've got 2 bonding pi 2p orbital electrons, and we've got no anti-bonding filled. Take the average, so that's equal to 1. So boron, diboron as a molecule exists. And so now we can go ahead and look at dicarbon. So does dicarbon exist? Arguably didn't need to erase all of that. But let's have a look. So dicarbon, we've just got the extra electron for dicarbon, which would mean it would go into the next orbital here. the next one up. So we've got, let's see, so dicarbon, we've got sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2. Then we've got pi 2p4. So we've got 6 electrons from each carbon. So we should have 12 electrons total. 2, 4, 6, 8, 12. The bond order of dicarbon would be, so now we've just got 4 here. So 4 minus 0 over 2, which equals 2. So this is the first time we've seen a bond order larger than 1. So not only does dicarbon exist, it's more stable than diboron because its bond order is larger. But it also means it has, according to this theory, a shorter bond. Because remember, bond order is proportional to 1 over bond length. So more stable bond, shorter bond. So dinitrogen, I've just added an extra p electron from dicarbon previously. So rather than erase all the good work we had with dicarbon, I can just go ahead and add the extra 2 electrons which go into the sigma 2p orbital. So that's the molecular electron configuration for dinitrogen. So now when we calculate the bond order, we have 4 plus 2 is 6 bonding electrons, no anti-bonding. We take the average, that's 3. So we know that not only does dinitrogen exist, but it's more stable than dicarbon. And it has, according to this theory, a shorter bond length. So we've exhausted this form of the diagram. Now there's going to be an energy flip between these orbitals. And now we have to go on to look at dioxygen over here. So we'll go ahead and do that swiftly. We've got the atomic orbitals. We can start to put in the 4th p electron for each oxygen atom. Okay. So we add 4 from here, 4 from here. So we follow Hund's rule and Pauli exclusion. So Hunt, Pauli, Hunt, Hunt, Pauli, Pauli. So how many is that? I need another couple. Hunt, Hunt. Okay. So I've got 3, 4, I've got 8. So 1, 2, 3, 4, 5, 6, 7, 8. Okay. Let's label these. So this is now the sigma 2p. This is the pi 2p. This is the pi star 2p. And we've got the sigma star 2p. So the electron configuration for the molecule O2 is now just going to be sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2. Then we've got sigma 2p2, pi 2p4. And now we've got pi star 2p2. Okay, so I've got my 16 electrons, 2, 4, 6, 8, 10, 14, 16 electrons total. The bond order is number of bonding minus anti-bonding, take the average. So 2, 6 total. Try not to write on the board. So 4, 6 bonding, and then I've got 2 anti-bonding. take the average. 6 minus 2 is 4. Divided by 2 is 2. So it exists. It's more stable than dicarbon, but it's less stable than dinitrogen. Let's do something before we go on any further. Let's look at something that you can often be asked. So if this is molecular oxygen, how about O2 with a plus charge? So let's take one electron away. If we did that, we would just take the last electron in away, so that would be 2p1. So there's only 15 electrons here, and that means we'd have to take one of these electrons away here. Notice I take a molecular electron away. I don't fiddle around with the atomic electrons. At least not initially. I will now, so let's take one away. Okay, if we did this, it would affect our bond order. So the bond order now, notice we've lost an anti-bonding electron, so this would now be 1. So this would be 6 bonding electrons minus 1 anti-bonding, that's 5. 5 over 2 is 2.5. So notice counterintuitively, by making O2 positive, now it's counterintuitive because oxygen is electronegative and it wants electron density, but by taking an electron away, we actually make something that's more stable because it has a higher bond order. So you could be asked, for example, in an assessment, which is more stable, O2 or O2 minus? Well, you would calculate the bond order. So I know that O2 plus compared to O2 has a greater bond order than O2. So I know that O2 positive has a greater bond order than O2, which means it's more stable, which means it has a shorter bond. Okay, so that's something that you can often be asked. Now let's contrast that with O2 minus. So let's go back to O2, but now we'll add an extra electron. So this is our original O2. To add the extra electron, we're just going to add it to the molecular orbital here, okay, which could be one of these. So now we'd have to go back and recalculate the bond order. So now we've, instead of taking an anti-bonding electron away, we've added 1, so that becomes 3. So if that becomes 3, then we've got 6 minus 3, which is 3, divided by 2, which is just 1.5. So now we can say, in terms of stability and bond strength, etc., we can say that O2 positive is more stable, shorter bond than O2, but O2 is more stable with a shorter bond than O2 negative. So you can often be asked for a homodiatomic plus an extra electron or minus an extra electron. So be on the lookout for how to do that. Just before we move away from O2, so I've gone back to our O2 molecule, our original one. So we notice that it's got 2 unpaired electrons. So there's no downward pointing electron. So O2 we can see has 1, or well, it's actually got 2. But by definition, if you have 1 or more, so it's got 2 unpaired electrons. If you have at least 1 unpaired electron, it means that you're paramagnetic. In contrast, if you had no unpaired electrons, if everything was paired up, like here with nitrogen, so dinitrogen has 0 unpaired electrons. So let's go ahead and write that real quick. So N2 in contrast has 0 unpaired electrons. Well, this means it's diamagnetic. It's important to be able to label these structures like this because this paramagnetic essentially for our purposes just means magnetic. So typically in chemistry textbooks you'll see a picture of frozen solid oxygen between two magnets, and the author will be trying to communicate that, hey, oxygen is magnetic, did you know? But nitrogen is not. It's not because it has no unpaired electrons. This becomes important later on in general chemistry. It's built upon in a second sequence of general chemistry. But at this early stage in general chemistry, we just need to note it. Diamagnetic just means not magnetic. And that's essentially all we need to know at this stage. Just be able to label and know how we can label based on the presence or lack thereof of unpaired electrons. Okay, to wrap this up, we've just tipped over the hour, so I'll try and wrap this up in a few minutes. We've got F2. I've added the 2 extra p electrons, so there's 5 p electrons from each contributing F. So we'd have sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2, and then we'd have sigma 2p2, pi 2p4, pi star 2p4. Our bond order, we can start to see that we have 6 bonding electrons. We have 4 anti-bonding electrons. Take the average. 6 minus 4 is 2. 2 divided by 2 is 1. So we have something that's definitely weaker than an oxygen, a dioxygen bond, and about the same as a dicarbon bond. Notice this is diamagnetic. There's no unpaired electrons, so difluorine, although it exists, is not a magnetic structure. And then finally, let's look at dineon, if that's a real thing. Well, dineon, we'd have to add our final, we'd have to fill the valence shell. So we've got 2 extra electrons. So now we'd have the addition of a sigma star 2p. And we've got 2 electrons there. So there's our 20 electrons total. 2, 4, 6, 8, 10, 14, 18, 20 electrons. And we've got total symmetry here. So I've got 6 bonding and 6 anti-bonding. So they would cancel and they average to 0. So I know that dineon does not exist. Remember, dihelium didn't exist, dineon doesn't exist, there's no bond order. And notice that these both have that in common, they're both noble gases. Noble gases, at least these 2 members of the noble gas family, don't associate with other elements. So this will wrap up this video on an introduction to bonding in diatomic molecules.